Welcome to G Fun Facts Online. Today, we are diving deep into the subatomic world to discuss a ghost. In the vast debris of a machine built to recreate the Big Bang, a fleeting apparition appeared. It survived for barely a fraction of a nanosecond, but its existence has rewritten the record books of physics. We are talking about Antihyperhydrogen-4. This is a clump of antimatter so exotic and heavy that its discovery is being hailed as a major milestone in our quest to understand the very fabric of the universe. To understand the magnitude of this discovery, made at the Relativistic Heavy Ion Collider, or RHIC in New York, we have to start with the fundamental mystery that haunts modern cosmology. This is the case of the missing antimatter. For decades, scientists have hunted for the mirror universe. According to our best theories, specifically the Standard Model of Cosmology, the Big Bang should have produced equal amounts of matter and antimatter. In 1928, physicist Paul Dirac formulated an equation that combined quantum mechanics with special relativity. It was brilliant, but it had a quirk. It allowed for particles with negative energy. Dirac realized that for every particle of matter, like an electron, there must exist a mirror particle with the same mass but opposite electric charge. He called it antimatter. When matter meets antimatter, they annihilate instantly, releasing a burst of pure energy. This is not just science fiction, it is a daily reality in particle physics. Even bananas emit tiny amounts of antimatter, specifically positrons, as they decay. PET scans in hospitals use these antiparticles to map the human brain. But here is the problem. If the Big Bang produced equal amounts of matter and antimatter, they should have annihilated each other completely in the first instance of cosmic time. The universe should be nothing but a sea of light. But that did not happen. We are here. The stars are here. Roughly 1,000,000,001 particles of matter survived for every 1,000,000,000 particles of antimatter that were destroyed. This tiny imbalance, this broken symmetry, is the reason existence is possible, but physicists do not know exactly why this happened. To solve this, researchers need to study antimatter closely. They need to see if there are subtle differences between matter and antimatter that could explain why matter won the war. But you cannot just catch antimatter in a jar. It explodes upon contact with air. You have to make it, and to really test the laws of physics, you have to make it heavy. That is where Antihyperhydrogen-4 enters the story. In August 2024, researchers found the heaviest antimatter nucleus ever synthesized, but Antihyperhydrogen-4 is not your garden variety antimatter. It is a hypernucleus. To understand what that means, let us look at a normal atomic nucleus. Usually, nuclei are made of protons and neutrons. Protons and neutrons are made of up and down quarks. A proton has 2 up quarks and 1 down quark. A neutron has 1 up quark and 2 down quarks. That is the standard recipe for the matter we interact with every day. Antihyperhydrogen-4 is the anti-reflection of a very specific, unstable isotope of hydrogen. Its composition is like a heavy metal band of subatomic particles. It contains 1 antiproton, which is the negatively charged twin of the proton. It contains 2 antineutrons, the neutral twins of the neutron. And then, it contains the special ingredient, 1 anti-lambda hyperon. A lambda particle is what we call a hyperon, which is a baryon that contains a strange quark. Or, in this case, because it is antimatter, an anti-strange quark. Strange quarks are heavier cousins of the up and down quarks. Their presence makes the nucleus hyper. Because the anti-lambda particle is heavier than a proton or neutron, Antihyperhydrogen-4 is massive. It is the heaviest antimatter nucleus ever detected, tipping the scales significantly higher than the previous record holder, Antihyperhelium-4. The extra mass comes directly from that heavy, exotic, anti-strange quark lurking inside. So how do you create such a complex, massive object? You need a machine that can melt atoms. This brings us to the Forge of the Gods, the Relativistic Heavy Ion Collider at Brookhaven National Laboratory on Long Island. This machine is a 2.4-mile atomic racetrack. It operates on a principle of brute force. It strips the electrons off gold atoms and accelerates the heavy nuclei to 99.995% the speed of light. When 2 of these gold nuclei collide head-on, the energy density is so extreme that it momentarily exceeds the temperature of the sun by hundreds of thousands of times. We are talking about trillions of degrees Celsius. At this temperature, the boundaries between protons and neutrons dissolve. The quarks and gluons inside them are liberated, creating a state of matter known as quark-gluon plasma. This plasma is essentially a time machine. It recreates the conditions of the universe as it existed microseconds after the Big Bang. In this cooling fireball, quarks and antiquarks condense out of the vacuum according to Einstein's famous equation E=mc². They frantically grab partners to form new particles. Most form pions, which are simple pairs of quarks. Some form protons and antiprotons. But in very rare events, particles group together in just the right way to form complex nuclei. To make Antihyperhydrogen-4, the chaotic soup has to spontaneously spit out an antiproton, 2 antineutrons, and an anti-lambda hyperon, all within a fraction of a femtometer of each other. They have to be moving in the same direction at the same speed so they can bind together before flying apart. The odds of this happening are astronomically low. It is a true needle in a haystack scenario. And yet, the star detector was watching. The star detector is a house-sized camera that tracks the thousands of particles erupting from every collision. It does not see the particles directly. Instead, it records their ionization trails in gas, measuring their curvature in a magnetic field to determine their charge and momentum. A research team led by physicists from the Institute of Modern Physics of the Chinese Academy of Sciences sifted through the data from 6.6 billion collisions. They were not looking for the Antihyperhydrogen-4 itself, because the nucleus is unstable. It decays after traveling only a few centimeters. Instead, they were looking for its fingerprint, the specific debris it leaves behind when it falls apart. When Antihyperhydrogen-4 dies, it undergoes a very specific decay channel. The antilambda inside the nucleus decays into an antiproton and a positive pion. This new antiproton joins the existing antiproton and 2 antineutrons to form a stable Antihyperhydrogen-4 nucleus. The positive pion flies off. So the researchers looked for tracks of Antihyperhydrogen-4 and positive pions that seem to originate from the same point in space, away from the main collision. This secondary vertex is the smoking gun. It proves that a neutral or charged parent particle flew out of the fireball, survived for a moment, and then decayed. After filtering billions of events, the computer algorithms found them. Amidst the noise, they identified 16 candidates. 16 might sound like a small number, but in high-energy physics, 16 clear events of such a complex antiparticle is a landslide. The statistical significance was undeniable. They had found it. Now, why does this matter? Why go to all this trouble for 16 atoms of antimatter? The discovery of Antihyperhydrogen-4 is a stress test for the laws of physics. Specifically, it tests Kaplan symmetry. This fundamental theorem states that matter and antimatter should be perfect mirror images. They should have the exact same mass and the exact same lifetime. The researchers measured the lifetime of Antihyperhydrogen-4 and compared it to its matter counterpart, Hyperhydrogen-4. The result? Their lifetimes were identical within the margin of error. While this might seem like a boring result because no new physics was found, it is actually a triumph for the Standard Model. It confirms that even in heavy, strange composite objects, the symmetry between matter and antimatter holds strong. If there had been a difference, it would have cracked the foundation of modern physics. Furthermore, this discovery helps us understand neutron stars. Hypernuclei are thought to exist in the ultra-dense cores of neutron stars. By studying how these particles bind and interact, even in their antimatter forms, scientists gain data on the strong force interactions that prevent neutron stars from collapsing into black holes. It also sheds light on the nucleosynthesis of antimatter. The fact that we can produce such heavy antimatter clusters supports a model called coalescence, where particles swimming close to each other in the cooling plasma clump together. This helps cosmologists understand how the first nuclei formed in the early universe. Looking to the future, the discovery of Antihyperhydrogen-4 is likely the limit of what we can find for a while. As you add more particles to a nucleus, the probability of creating it drops exponentially. To find the next heaviest antimatter nucleus, perhaps Antihyperhydrogen-5, we would need collision rates hundreds or thousands of times higher than what RHIC can currently provide. However, the ALICE experiment at the Large Hadron Collider in Europe is also hunting for these exotic nuclei, and future facilities like the Electron Ion Collider will continue to push the boundaries. In the flash of a gold-on-gold collision, humanity has glimpsed the mirrored edge of reality. We have forged the heaviest piece of the anti-world ever seen. While it did not solve the mystery of why we exist, it proved that our understanding of the mirror world is precise. We are capable of recreating the Big Bang. We are capable of catching ghosts. And in the 16 tiny tracks left by Antihyperhydrogen-4, we see the beautiful, terrifying symmetry of a universe that, but for a tiny roll of the cosmic dice, might have been made entirely of antimatter. Thanks for listening to G Fun Facts Online.